Hello, it's David. Viewers of my previous videos will know about my DFB1 project, David's Falcon Booster Type 1, and it's been an ongoing attempt to spec up my my Falcon 030 a little bit here by using an external 030 CPU clocked at 50 MHz with a load of TT RAM on top. And I've got to a point where it's nice and stable. However, it is a bit of a hack. So if you haven't seen it before, this is the DFB1 in action. And you can see here we've got a, it says 60 MHz, that's not true, it's 50. We've got a 68030 and a, pardon me, and a 68882 coprocessor there. And we've got, in this case, 64 megabytes of TT RAM, and we're running interlaced 256 color mode at the moment. If we have a look at GenBench, you'll see that I'm just going to compare this to an ST FM for now, because it's got some figures here that we can look at. There we go, we've got approximately a 17.5 times speed increase on our main processor, and the TT RAM, the Alt RAM, is a relatively impressive, give or take, about 830% speed increase. Now, okay, that's via an ST. What about if it was via compared to a Falcon? So it's only 311%, I'm afraid, on the integer division, and there's no percentage for the Alt RAM. That's why I actually compared it with the other one first of all. But this works very nicely, and I'll show you a little bit of how it looks. So, one of the key aims for the DFB1 project was that the board should be able to fit in the case with the original power supply, obviously not with the original shielding, but should be able to fit in the case with the original power supply, and it should be plug and play. We shouldn't require anything else. And this version here, which is the revision 4, does achieve this, although unfortunately it had some bugs in it, and I had to apply some bodge wires. So there's 3 bodge wires up here, there's a couple of cut traces and bodge wires over on the RAM side here, and there's another couple underneath. There's a few resistors and things hacked into place. This is running at 50 MHz. This FPU is capable of running at 40 MHz, and it's got a bodged on external oscillator to drive that separately, because unfortunately that won't run successfully at 50. But currently this is configured so that the FPU runs at half the frequency of the CPU, which is sufficient for my needs, and still yields some reasonable figures. Obviously, it's normally clocked, if you have one installed. They don't actually come on the stock Falcon. They're normally clocked to 16 MHz, so you're getting a nice 1.5 times figure on the floating maths. Anyway, again, this one doesn't have the percentage pre-saved. Whether we have one that does. There we go. So we've got 156% on the float maths. So it's a nice boost, and you can do quite a lot of nice things with this. So that was the DFB1r5 revision 4. That was the fifth technically iteration of the design, and it's the first one where basically all goals have been achieved reliably, but still has some bodge wires. So we need to move on from that. But I thought I'd take you quickly through the evolution of this project. This was the DFB1R1, just this little tiny board here. This had no attempt to do anything particularly clever. There was no acceleration intended. It just tried to get an external CPU, a little bit of logic, and a couple of SRAM chips just to prove the point. Now, it turned out that I got the configuration, the wiring of this all wrong, and whilst I could quite happily drive my external CPU, which was great, there wasn't really anything else that I could do with it. It was really very much, all intents and purposes, a learning step. I just got the wiring wrong for the RAM, and I was using at the time an Altera Max. Can't remember which version. An Altera chip anyway, 5-volt tolerant, and they discontinued it. So that one was the end of the road. So from there we moved on to DFB1r5, which is this one. In fact, actually I was still using the Altera on this one. When I designed it, I hadn't realised it was discontinued, and I really struggled to get a to get the chip in the end. So this one was of limited future development anyway, but this introduced an external crystal, main CPU, still had the two static RAM chips there. I think this is a grand total of 1 megabyte of Ultra RAM, but it was just for experimentation. And you can see there's a few bodge wires and things, but this one did actually work. We got acceleration, we got it running at 50 megahertz, and we got some SRAM. But only, this one was actually only 16, these are 8 bits of SRAM each, so this was only actually a 16-bit bus, but again, it was just to prove the case. So it wasn't particularly fast, wasn't as fast as it's ever going to be, but again, we proved that Alt-RAM could be brought online happily with a board of this form factor. So then we moved on to the DFB1r5, and unfortunately that one was not a success. I don't even have a partial build, I don't think, unless this is one over here. No, this is a Rev 3B. Yeah, no, unfortunately, the problem I had with the Rev 3 was that I designed it. I decided to take a step sideways and try a design with a quad flat pack chip instead of the PGA, because I found the PGA very troublesome. But the quad flat pack chip doesn't run as fast, and it was an absolute beggar to solder. And I went and got my footprint wrong, so it was completely useless. So this was the next one. This is the DFB1r3. I think I'm missing one. There's an R3B somewhere. Where which? Yes, no, this is the R3B. So revision 3B, second attempt. So here was the first time that we brought in SD-RAM. So these two are actually the same. So we brought in SD-RAM for a much larger size. One of these is, I think, 64 megabytes. One of these perhaps is 128. I think this is 128, this one. So I could support different sizes. This one I think was, maybe this one was only 32 actually, this one. So this brought in some additional features. This brought in, obviously, the CPU is still here. We've switched to Xilinx now. Which, to be honest, I don't like as much as the Alteras, but these ones are at least still obtainable. We've got our external crystal still. We've got buffers now, 4 buffers for the 4 different 8-bit memory banks of the 2 chips here. So it's now full 32-bit memory, which means we can run a lot faster, use S-term. We brought in a flash ROM over here so that we could use our own operating system built into it, and I've got some status LEDs down the bottom, and that was so successful that I built a second version of that. But you see there's still a couple of bodge wires and things on there, quite a few on the bottom. That was so successful I built a second version, managed to reduce the bodge wires down to a smaller number by planning ahead there. But this one was just really an evolution, make sure that I could build a second board. That one worked, that one was perfect, 128 megabytes, full speed. That was the target, complete, but it didn't fit in the case. It was a bit too big. All the debug headers on here. This was just to prove that I could build a second board and it would work. It did, and so it was time to move on to the next design, which was the one that we see in the Falcon here, which was the DFB1r5. So, what about today? Why are we here? Well, I'm going to introduce to you the DFB1r5. This is, hopefully, the bug-fixed version of the one that we've just demonstrated in the Falcon there. And I need to start building it up. So we've got our FPU, we've got our CPU, we've got the same CPLD as in these, we've got the same RAM chips and buffers as in these, we've got an optional flash chip up here. we've got the main crystal for the CPU, and down here we've got an optional second crystal for the FPU if we want to run that at a different speed. What I found is that we can run the FPU anywhere between approximately half the CPU speed and the full CPU speed, but it has to be able to support it. So for example, I've got a 40 megahertz FPU, and you do have to test them. Sometimes they look like they pass, but then if you run all of the tests, it will fail on one or two. So I've got one that runs at 40, one that runs at 33, and one that doesn't get past 16. So for example, I could put a 40 megahertz crystal in here and get the maximum out of my combination of hardware, or optionally I can instead run with what I'm doing now and put in one of these resistors in place, and it will run at half the CPU speed. So we've still got our status LEDs, and there's an awful lot of passive components that need to be soldered on the back. So today, this is the first part of hopefully a short series where we go about building this up, and then we see if we can bring it up. Okay, the reason why I'm doing this in parts is twofold. One, I don't think I'm going to get it all done in one day, and two, I'm not sure that I've actually ordered all the parts for this yet. I may have to do some scavenging. I've got some old boards here. I'm going to have to nick the regulator off, for example, and my buffer chips, things like that. So we'll be going piece by piece, and what we'll do is we'll try and get it initially to a point where it will boot with no FPU, no Ultram, no flash, and add to it hopefully as we go. So what I'm going to start with first, I know the general recommendation is to always start with all the passives on the back because they take a long time and they're nice and low profile, and then it will sit level while you work on the other side. But I personally always start with the CPLD. The reason for that is the easiest one to get wrong. If you make a terrible hash, you've only soldered one component, and we can ditch that board and move on to a new board. So I've got my CPLD here. This is a Xilinx XC95288XL in a 144 pin configuration, and it is by far the hardest thing on the board to solder. So we'll look around here. We can see the pin 1 marking is just up in the corner nearest you. That's pin 1. It's got an extra line there. The others don't have that line. And pin 1 on the chip corresponds, slightly surprisingly, to the bottom corner there, the bottom left corner as you're looking at it, where the dot is. So we need to get that lined up with that. Being very careful of these pins. Oops. And many's the time that I've soldered, just catching on the board here, many's the time that I've soldered all the pins and then realised that I've jammed one into the other in one of the corners, and it's a write-off. You can't fix it once you've gone around and soldered. You have to completely take the chip off, and normally it's a new chip. So I don't have a microscope. What I use is this head-mounted pair of lenses. I suppose you'd call it a loop. And so you're going to have to excuse me a bit while I get in and examine this for alignment. There's one pin in the corner here that's causing me some concern. It's probably okay. No, they don't seem to be sitting very flush, is my concern. So I think we might have to anchor it down, and then as we solder, hold it down, flush it to the board. But I can't see any that are obviously bent sideways, but one maybe bent a bit lower, causing it to ride high. That's not too bad with a little bit of pressure on it. Okay, so the trick now is we take our solder paste and we try and anchor corner. Nice big blob of paste. Oh, I've nudged it. Paste won't come off. When you see someone like Gadget UK 164 doing this, he plonks it on the board and he does his soldering, and he grumbles about it a lot. Everyone does. It's not easy. But the one thing he does always seem to get very quickly is the alignment, and it is, for me, impossible. I bet there's a lot of work off camera. Fair amount of swearing too. Okay. So my personal preference for these sort of things is this is a K-tip, shaped like this. It's got a wedge down the middle, but a nice large area for good for drag soldering. And I'm going to get a nice big old blob on the end of my tip. In fact, actually, I'm going to clean that a bit more. Nice big old blob on the end of my tip, and I'm just going to get messy on the corner of this one and try not to move it again. There we go. So that is not a pretty bit of soldering, if I can get that in shot, but that should anchor one corner. Now I can go around and recheck all of my alignments again, and then I'll be doing an opposite corner. Okay, so now we move on to doing one of the sides that has not been anchored. So get that back in focus. I'm being absolutely over the top here with the amount of flux, but flux is what simplifies the job. Just triple, quadruple check my alignments, as I am so nervous about that. Okay, here we go. So slightly less solder this time, and we'll have to top it up on a couple of occasions. And it should flow because of all the solder, because of all the flux. I forgot to apply my downward pressure. And that doesn't look too bad at first glance. There's maybe a bit of a dry joint in the middle. She'll come back and inspect that in more detail later on. That's our first side, and then we'll do the same on the opposite side. And obviously we just continue round. That doesn't look too bad. Let's give that a quick clean up. The problem with using so much flux is that it does leave a horrible sticky residue that's very difficult to clean. Look at all that gunk on there. But as I've said before, I'd rather be a bit messy and have a high yield and be neat and tidy and keep throwing boards away. Well, and these chips at the moment, these cost about 20 quid a pop, so it's the single most, apart from the CPU, it's probably the single most expensive item on here, so let's look after it, eh? So I'll do a proper buzz test on these, just go around with my multimeter in continuity mode to see if any of the adjacent pins are shorted, but that's a fairly dull old process, so I won't do that on camera. I will, however, just take the time to do the most elementary of checks, which I always recommend, which is the short to ground check. So this particular chip is driven by the 3.3 volt rail. There are two power rails on here. We've got the 5 volts that comes from the Falcon power supply, and we've got the 3.3, which the memory and the CPLD run off. So we'll put this into continuity mode. So we can get this into shot. So what the first thing we're going to do is we're going to look for the ground line, of which there is a test point there, and the 3.3 volt line, which there should be a test point there. No short. That's good. In fact, I wonder if it's got an ohms reading, I should say. Should come up with something, because there is a chip across it. No. Try that again. There we go. So it's reading 5 megaohms. So there's something across the line now, which is good. We're expecting that. And what I would do genuinely is I would start on one pin there, and go across one at a time. But it's very difficult because the probes are big and the pins are small. And there, for example, I thought I had a short and I don't. No, that's me touching the probes. You get the idea. That's going to take a long time, and I should do that off camera. But good, so that seems to be our first hurdle out of the way. Of course, I say I need to inspect it more thoroughly and make sure there's no dry joints there, but I can't see any shorts and the alignment appears good. So The next most important things, I think, are, as discussed, the passives. Now these are unfortunately not the most fun things in the world to solder because there are just so many of them. What I need to do is to get my, that's not it, get my bill of materials so I can make sure I know which resistors are which values. There's a few jumpers here as well, connected jumpers. These are for optional changes. So for example down here, jumper 7, this connects the CPU bus grant in, CPU bus grant out lines. This is where the jumper on your Falcon is normally shorted across, and I have it normally shorted because I rely on the lower priority bus grant pin from up here. However, you may wish to stack a board on top of this if that's your want, and you perhaps need to interrupt that. So you've got the option to snip that. Down here we've got the option to snip some certain things if we want to provide continuity, because I think, for example, A1 doesn't get passed through to the FPU. So if you wanted to pass A1 through and say use that as an expansion header, which you could do, then that gives you the opportunity to cut the pull up and connect directly. And there's another few around here where again you can cut the pull up and wire something into. I think that's probably the cache inhibit pin, and so it'll let you do some other optional features there. But I think these the majority of these passives and the resistor networks I probably need to get on with, even if I only do the ones that I'm interested in today. So like the CPLD, the CPU, and the resistor networks. I think we need to start somewhere. Maybe I'll even do the LEDs. We'll see how far we get. Okay, so we're starting on the bottom with our passives, and the majority of the capacitors are going to be 100 nanofarad, so that's what I'm going to start with. I've got my, in lieu of a bomb, I've got my, what do they call them, fabrication drawings. So I'm going to start with the bottom end. You can see that we've got 100, 100 and 2 10s around there. On the bottom of the CPU we've got 100, 100, 100 and a 10, I think that is. Maybe that's a 330p there. I'll have to double check that. And there's a few dotted around the place. So this is what I'm going to start working on now. So my technique for doing passive is quite basic. Just going to drop out a couple of these because I intend to do 2 for now. And what we'll do, I'm going to do these 2. So what we'll do first is get a little bit of flux on that, a little bit of solder, get the cap in the tweezers, line it up on one side and just dab in. Hold it in place, dab again, turn it around and repeat the process. Done. It's not the neatest, it's not the tidiest, but it's fairly quick and simple. And with as much flux as I've put into place there, it really is quick. Two down, 1 million to go. And here you can see the problem, because I've soldered that CPLD on, the board is now unsteady. And as you press down on it for that second pass, you can hear it click quite often. As it levels out. See if you can pick this up. I'll just turn the extract fan off for a second. See if you can pick this up on my mic. So pressing down on it now, I'm going to dab in. There. Did you hear that? I've just decided I'm going to do all the 100 nanos while I've got them out. Won't hurt. This one here is actually only required if I'm using the second crystal. But again, since I'm here, I'm going to fit it and it doesn't hurt. In fact, technically it probably isn't even required if I'm using the second crystal. Just for as an abundance of caution, we've got a decoupling cap across the crystal's legs. The previous iterations haven't had a decoupling cap on the crystal, on the oscillator I should say. Right, it's also got the R1 there. I'm not going to fit R1 this time. Right, I think that's all the hundreds. Is there any 100 on the top? We've got a resistor. That's for the clock lines. I don't think there's any capacitors at all on the top. Two more resistors there. R18 to be removed if using X2, yep, so I will populate all of those. Those will be with low impedance resistors, probably something like 33 ohms. Okay, those are resistors, those are resistor networks. Right, so we've got a few 10 microfarad yeah, we've got a few 10 microfarad caps. We've got two there, those are 10. We've got one there, that's a 10, and we've got one there, that's 10, and we've got 330 pico as well. So that's us done with the 100. So cap, 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 missing. Pardon me. Cap, 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 cap. So I think that's everything bar our 330 picofarad. Now this one's going to be slightly different because I've already got a bit of solder on the pad. I could wick it up and go from there, but I really don't think it's necessary. I should just be able to tack onto it and then snap it into place the same as before. But obviously it will start at a much higher angle. Well, tweezers get covered in flux, unfortunately. There we go, and then just snap it back into place as with the others. Anyone who tells you through-hole soldering is easier than SMD is a big fat porcupine spinner. Bosh, bosh, bosh. Right. Just have a quick inspection. They're all really gooey and gummy at the moment because of the excessive amounts of flux that I like to apply. So there we go. Can't see any missed ones. So what about our straight resistors? I don't like to do the resistor networks. I find them very awkward. So let's do we'll do those last. So the straight resistors, what have we got? We've got a couple of 2K2s. Don't think there'll be many of those. There's obviously pull-ups on high speed lines. These SMD components, by the way, these are all 0805s. I can't remember what that is in the metric. But these aren't too bad to do if I was working in a much tighter space. I think, for example, on the ST booster I'm doing, where I'm trying to fit it all into the same size as or almost the same size as a 68,000 processor, then going down to the 0603 might be convenient. But I've got a big book of 0805s, so that's what I'm going to use until it becomes an issue. And they look alright. So what else have we got here? We've got all of the optional resistors. So these resistors across the top here, these are all in case you experience instability with some of the control lines. So I think these attached to, for example, the bus grant acknowledge, the bus grant, the bus request, and the reset line. I think the one on the end is the reset line, so that's probably the only one I'll populate to start with. So that one's normally a 4K7, I think, and the other's normally 10K. These ones down here are for the LED displays. So they're nominally 1 kilo ohm. 680 would do. Depends how bright you like your LEDs. I just want to see that activity is occurring when I'm expecting it to. So they're more just for indication. Once you've got the keyboard in place, you can't see them anymore anyway, so that's a bit a bit of a waste in that case. Right, so let's get on with the 1Ks. Experience any problems with the reset system, then the first thing to do is take this off, see if it gets better or worse. We can always put a lower or higher, I should say, value, a less aggressive pull up on it. But I have found that this does help once you've got a load of extra loading on the system. Okay, so I'm not going to populate those optional ones. And we've got some optionals on the well, not optionals, but tuning resistors on the front. So we've still got our networks. We've got 1, 2, 3, 4, 5, 6 resistor networks. I'm not actually sure I've got any of those. Those are 4x10K, and they're used primarily for doing pull-ups. Okay, so I need a few 33 ohm resistors, and these are used to debounce or clean up the inline termination for the clock lines. So there's one here for this clock line, there's one here going out to the SDRAM, and there's one here going to the... Actually no, both of these are needed, because one's going to go to there and one's going to go to there, and what we might do is remove that and fit another crystal instead, another oscillator instead later on. So let's take a few of these out. This is the main 50 megahertz input line, that's the 50 megahertz SDRAM line, that's the 50 megahertz CPU line, that's the 25 megahertz FPU line. Okay, so any more passives on the top here? 1, 2, 3, 4. And any more passive on the bottom? Those I'm not going to fit. 1, 2, not going to fit that one yet. I suppose I could. No, I won't. Shall I? I'm here. I'm here. It's a 33. I'm doing 33s. There. Why don't I? This is for the FPU oscillator, so if there's no FPU oscillator actually fitted, it's totally irrelevant. But it'll be one less thing for me to solder if I do fit myself a 40 megahertz oscillator down the line. And to be honest, I probably will. That's why it's here. Might as well test my own board, won't I? Right, so one, two, three, four, five, six resistor networks to do, and I've got to do the can't think what it's called. The voltage regulator. I don't actually have any spare voltage regulators, so I'm going to actually steal this one from this board here. So because I hate resistor networks so much, I'm going to maybe come back to do them next time. But for now, let's see if we can get this voltage regulator off with a bit of braid. Normally I just do this with hot air, but it's so close to the what do you call it? So close to the board interconnect there, it would just melt it. Which I don't intend to use it again, but it seems a shame. No, I think it's going to have to be hot air. So we're going to want a little bit of Captain tape. Hot air station ready. So we'll whack that up to about 350, and that'll have it off in probably a second. Just because I've wicked away most of the solder already. So we'll just captain off that a little bit to see whether I can save that. Not that I intend to use this board again. This was actually just a test jig to see whether I could get a 144, an XC95 144 CPLD to hold all the equations, and the answer was no. Okay, so bit of hot air. Just try and pick up the board from the regulator itself. There it is. Not quite a second, but not far off.